Hello everyone. So in this video, we are going to talk about the topics of linear approximations and differentials. So we start by having an analogy. So this is what is stated in the slide. We have seen that a curve flies very close to its tangent line near the point of tangency. Okay, in fact, by zooming in toward a point on the graph of a differentiable function, we notice that the graph looks more and more like its tangent line. So basically, this is how we phrase the problem of linear approximation, how we describe linear approximation, where we actually use the concept of tangent line, or we build the tangent line from the idea of differentiation. And then from there, we are using that tangent line as an approximation to the curve. And of course, it is very practical. It can be used when the point that we are considering on the tangent line is close to the point that we are approximating. Okay, let's say we have 0.1, for example. So point close, very close to the value 0.1, okay, we are going to get a good approximation. But of course, it depends on the curve itself. Okay, and generally, when we travel further from that line, the approximation, sorry, when we travel away from that particular point that we use to construct the tangent line equation, okay, we are not going to get a good results of approximation. All right, so you can imagine something like this one in analogy. So when we talk about the concept of globe Earth, or something that we are commonly referring to as sphere, okay, we know that the Earth is a sphere, but when we zoom in as much as we can, for example, we are looking from our naked eye perspective, we are actually seeing that the world is sort of laying flat, right? So this is also close to the concept of linear approximations that we try to bring in here, right? So normally we look at the Earth, something like this one, but when we keep zooming in, okay, closer and closer, we are getting something that looks like a flat line, okay, a flat surface. Okay, maybe this is the idea that has been brought by the flat earthers lah. I believe so. Okay, so in mathematics we can relate, okay, what is the perspective of the flat earthers, okay, in terms of discussing or describing an event through our naked eyes. Right, so this observation of the concept of tangent line as the approximation for the curve is the basis for a method in finding approximate values of functions. Because in real life, sometimes it's not easy, okay? Not that I'm saying it is not practical, but it's not easy to find a value that is on a curve, okay? And at times, we require this kind of approximations, okay, to help us, find a good value to be used at the point that we have difficulty in finding the exact or the actual value. Right? The idea is that it might be easy to calculate the value of fa of a function at a particular point, okay, but difficult or maybe sometimes even impossible to compute nearby values of f. Okay, it's easy for you to compute, for example, value fa when a is equal to 2, but when you increase a bit, maybe like 2.1, 2.05, for example, it's difficult to compute. Then you rely on linear approximation. All right, so this is the figure that I said just now. Okay, we have a curve. Okay, that's the blue figure, the blue line that we have in this figure. And then we have the tangent line that is being given by this pink line, okay, y equal to Lx. Okay, and we are using that line y equal to Lx as an approximation. So if I try to zoom in this figure, okay, so you can see here, if I'm constructing the tangent line at this point, of course, at that particular point, the value of A and FA will be the same if you consider either the tangent line or the curve itself. But when you go further, so you can see if you go, for example, at this particular point, you are using the tangent line as an approximation, right? So you see there is a bit different between the point on the tangent line, the value, all right, and the actual value of the curve that is here, right? And as you go further, for example, this point, okay, you got something that is having bigger gap, okay? And generally speaking, and when you go further and further, you are not going to get a good approximation. But that is only for general case, because it's also possible to have a case that is oscillating, right? You might be crossing the tangent line from time to time. So that's the general way we describe why, and the reason we are using the tangent line as the linear approximation for our curve. All right, so we are going to define Lx later on as well. All right, so in other words, we use the tangent line as the approximation when x is near A. So this is the equation of tangent line. We have used this a lot previously. We have y equal to fa plus f prime a x minus a. So if you want to, have some sense in terms of finding tangent, you can have y minus fa over x minus a equal to f prime a. So that is the equation of the tangent line, not the approximation yet. Okay, and the approximation is given by fx. And then we use this approximation approximately equal to fa plus f prime a times x minus a. So they are basically the same thing here, but now we are just considering the values for the approximation. And we call this equation or this approximation as the linear approximation or simply tangent line approximation of f at a. So basically they are the same thing. One, you have a linear function, there is a straight line, and then you also have the tangent line. All right. So the similar approximation. Now we use the equal sign. Okay, we say that the linear function worth graph is the tangent line that is given by the same equation or expression on the right hand side, fa plus f prime a x minus a. But now we have Lx instead. It's called the linearization of f at a. So it's easy for you to remember the equation or the formula here because they are basically the same thing, just that the first one is we use fx, and that is the linear approximation, and the second one we use Lx, that is the linearization of f at the point A. Okay, so let's take a look at one example to give you, a good understanding on how this linearization works. So we are going to use the equation that we had in the previous slide. Okay, so we want to find the linearization of the function fx. Okay, fx equal to square root x plus 3 at the particular point a equal to 1. Okay, so that is where we are going to construct our linearization, and we are going to use it to approximate the numbers. First, square root 3.98, and then square root 4.05. Okay, and we want to see whether this approximation overestimates or underestimates, because of course, okay, in reality we can just compute these two square roots using our calculator, and we are going to compare the result there. All right, so first, in finding fx, okay, the approximation or the linearization, we need to know the derivative, that is f prime x. Okay, so I think it's pretty easy here. You just use the simple chain rule. So you have x plus 3 to the power of 1 over 2. So upon differentiation, we are going to have the n 1 over 2. And then the same thing, the argument x plus 3. And then the power of 1 over 2, you're going to minus 1. So we are going to have negative 1 over 2. Or you can simply rearrange them into this form. 1 over 2, and then you can have this square root x plus 3. Maybe that is easier for you to compute. And then we want to construct the linearization at the point a equal to 1. So we have f1 that we need to find. So you just simply plug in the value, square root 1 plus 3. Okay, so you have square root 4 that is equal to 2. And then you need to find f prime 1 by substituting the value x a equal to 1 inside here, a equal to 1 in the place of x inside here. So we have f prime 1 equal to 1 over 4. And now we are going to use the formula for the linearization that we had just now. That is Lx. So Lx is equal to f1 plus f prime 1 times x minus 1. So you can bring the values here, and then you have x minus 1, and the one that you are going to obtain is 2 plus 1 over 4 x minus 1, and upon simplification or expansion, you are going to have 7 over 4 plus x over 4. Okay, so this is the linearization that we obtain for this particular problem, and then we are going to use it to approximate the numbers, right? So the way we are going to approximate this, we write it like this one: square root x plus 3 approximately equal to 7 over 4 plus x over 4. And then from this formula, we are going to get square root 3.98. Okay, so you can write it in this form, that is 0.98 plus 3. Okay, 0.98 plus 3, and that will be equal to, you just plug in the values of 0.98 inside this particular formula. So you have 7 over 4 plus 0.98 over 4, and that will give you 1.995. All right, and then you can repeat the same process for, let me put it here. Okay, for square root 4.05, and then you translate it into this form to check what is the value of x. So you have square root, okay, what plus 3, that is 1.05 plus 3. Okay, and you do the same thing here, and then you are going to get that the value here is 2.0125. So you can see the two differences. Here you are starting at 1, but here you have 0.98, that is 0.02 away from 1. And then here you have 1.05, that is 0.05 unit away from 1. So this one is 0.02, meaning that this one is closer. All right, and then we say that the linear approximation, okay, we can try to illustrate it into figure. So this is the figure that has been prepared for you. All right, so we can see from this here, okay, we have the value and everything here, that the tangent line approximation is a good approximation to the given function when x is near to 1. All right, and if you want to try to plug in the values on the calculator, you can make a comparison. Okay, the calculator will give you approximation for square root 3.98 and square root 4.05. Okay, but the linear approximation that we did just now give an approximation over an entire interval instead. All right, even though when you get further from the point where you construct the linearization or the approximation, you're not going to get something that is good lah. Okay, depending on the curve, of course, because sometimes we have the oscillation of the curve. All right, so in this table, we present to you some of the values that we obtained from the linear approximation and also the actual value so that you can see the pattern. Maybe we can take a look at one of the direction. Of course, this is where we start we use the point x equal to 1 for generating or constructing the formula for linear approximation. So of course, there are two directions, this one and this one. But let's take a look at the more complex one, and we can do the same for the one that is going lower here. Okay, so you can see here when we have the value 4.05, okay, x is 1.05, that is like 0.05 away from 1. Okay, and then we have something bigger. When you have 4.1, x is equal to 1.1. When you have 5 here as the argument here, we have x equal to 2. And then here for 6, we have x equal to 3. And these are the values that we obtained from the formula linear approximation that we had just now. So you can see here, okay, the difference that we have here. So we consider this one to be the closest lah, this one to be the furthest. So you can see the actual value when x is equal to 1.05 and try to plug in the original formula, you'll get that the value is 2.0124617 and so on. And from the linear approximation, we get that the value is 2.0125, right? So you can see the difference, okay, the error or the gap between the actual value and the linear approximation is pretty close. So you can see the first place here, second place, and third place here is the same as the actual value, only that the fourth one, okay, different from, sorry, the fourth one different by like 0.04 only. Okay, so I'll put here the difference is around 0.04 approximately. And then you can see as we move further, the x become 1.1. For example, you have the approximation to be 2.0255, and now the actual value is 2.0248457. All right, 567. So you have here the first one's the same, the second one is the same, but now the third one is no longer the same. So it is the gap or the error is approximately 0.00, I would say, not 0.0. This one is not. This one is 0.0004, sorry. This one is 0.002. All right, approximately lah. But you can see if you are not sure with my calculation here, my approximation here, it's better for you to plug in your calculator and get the exact gap between the linear approximation and the actual value. But the thing that I want to highlight here is that you can see the difference, okay, between the linear approximation and the actual value when we are closer to the value x equal to 1 is very small, 0.004. And as we move further from point x equal to 1, now we have the difference is 0.1 rather than 0.05 that we had earlier. Okay, the gap, okay, the distance between the approximation and the actual value grows bigger. And you can try for the remaining two values and you see that it gets bigger and bigger. All right, so you expect that if you move further, if you don't have the specific figure function like the oscillating one, okay, you can expect that it will always get bigger and bigger lah. But then in general that is the case. But then specifically we have to see it from case by case basis. All right. Okay, so this is the figure again. Okay, you can see the pink line is the tangent line. And then the blue line here is the function itself. And as we move away from the point that we construct the formula, you can see the gaps getting bigger and bigger on both sides. Okay, it does not have to be uniform. Okay, in moving to the left direction here, you can see that the gap is much bigger here, but the gap here increasing slowly compared to the left hand side. But that's not the problem lah. That depends on the function. But when we get very close, sufficiently close to the point x equal to 1, the gap between the tangent line and the function value, the original function value, the actual function value will be almost similar. That's why we say that the approximation is good when we are close to the point that we construct the linearization formula. Okay, so let's now move on to the next subtopic that is on differentials. All right, so differentials, we want to bring the same idea, okay? The idea of approximating values. But now we use the concept of differentials. I have touched a bit about this in our class, okay, and also in the beginning of the chapter integration. Remember, when we first do the integration, we translate it into indefinite integral. Dx, dy at the back don't have specific meaning. Okay, but we know that it is originated, okay, the Leibniz notation from delta x that we use to calculate the rectangle, the base, okay, the base of the rectangle, okay, that we use to calculate the area of the rectangle. So basically, that's the idea that we want to bring here in discussing about differentials. Okay, we want to give a sufficient meaning to differentials so that we can do the one that we did when we discussed about substitution rule. Okay, meaning that you can bring the dx to the right hand side because we are treating it as a number. All right, so the ideas behind linear approximations are sometimes formulated in terms of terminology and notation of differentials. Okay, linear approximation, okay, formulated in notation of differentials. Okay, we say here if y equal to fx, where f is a differentiable function, okay, we need that criteria, differentiable. Okay, then the differential dx is an independent variable. Okay, meaning that the changes in x, okay, or the changes in delta x, for example, later on, it will give effect on the values of the function. And in case of dx, it gives effect on the value changes that happens to the tangent line. Okay, dx can be given the value of any real number. Okay, because now we are giving meaning to dx, meaning that if you have initially you have dy dx equal to f prime x. But in the first place, when we did the differentiation, okay, we don't have the specific meanings of dx. But now we give a notation of differentials. All right. Then dx here can be given the value of any real number. And if it is a real number, we can perform algebraic operations, meaning that we can get to this form where we actually, okay, multiply with dx on both sides. And we have dy equal to f prime x dx. So dy here is the differential as well. Okay, we have two differentials here, differential dx and differential dy. And differential dy is given as f prime x dx. Okay, so dx here, you can think of it as a function lah. You have dx as the independent variable here. So you make changes to dx, because dx is a number. The value of dy will change as well. And the f prime x here is the slope of the tangent line. So we use dy here, okay, to approximate of the value of delta y. But first we have to understand what is delta y, what is dy, what is dx, and what is delta x. So we can refer to this figure here, okay, to understand the geometric meaning of differentials, every single one of them. And of course, the first thing that you need to know is that dx and delta x, both of them are independent variable. They are actually the same. Okay, but later on when you go to function of several variables, okay, you have x and then you have y. Both of them act as the independent variables and give effect on the subsequent variable, dependent variable. That is, we have x, y, z. So x, y independent, z is the dependent variable. But now it's okay. Let us focus on function of single variable first, where dx is equal to delta x. Okay, so delta x here is technically the difference lah, the changes that happen to x. Okay, when it move from x, this point, to x plus delta x. So the calculation of dx and delta x is basically the same. All right. So delta y and dy, they are different. So that's why in the previous slide, I said that dy is being used as an approximation. dy as approximation for delta y. Okay, first we have to understand what is dy and what is delta y. So to make yourself easy, dy here is something, okay, or the changes related to the tangent line. And delta y is the changes related to actual function. Okay, because the pink line that we have in this figure is the tangent line and the blue one is the actual function. So what is delta y here? Okay, delta y here is the changes of value. And the value that you use here, there are two things. Okay, the first one is the function value. Function value, not the tangent line. Fx plus delta x minus the function value at the initial point. That is when we have this p lah, to be considered as our initial point. So we have fx plus delta x minus fx. Okay, so this is our delta y, the actual change. Right? And then we also have dy. Okay, so geometrically speaking, dy is the changes that happen to the tangent line. So you can see, okay, let's say our function is, for tangent line, we have gx, for example. Okay, so this will be gx plus delta, I'm sorry, I want to use dx lah. Okay, but they are the same thing because dx is equal to delta x minus gx. So the increment here, you can see, this is the dy and this is the delta y. Okay, but we don't really want to use this one. We want to use the formula that we had earlier. That is dy equal to f prime x dx. But if you use this formula, is it wrong? Of course, it's not wrong. Okay, but it requires you to find the equation of the tangent line first, okay, before you can plug in the values. But here, you don't have to find the formula for the tangent line. Okay, you can just use the derivative, that is f prime x, and then you multiply with the increment, okay, x plus delta x minus x, and then you'll get the differential dy. Right. So let's take a look at one example. So this one is the same thing that we discussed earlier. So this example to illustrate, okay, what is the the concept of approximation that is being used for this topic. So we want to compare the values of delta y and differentials y. If y equal to fx equal to x cubed plus x squared minus 2x plus 1, and x changes first from 2 to 2.05. Okay, meaning that the changes happens to x here is 0.05. And then the second one, we want to compare what happens when x changes, okay, from 2 to 2.01. So the changes is 0.01, meaning that the second one is closer lah to the point that we construct the tangent line, sort of. All right. So let's just begin with question A. Okay, question A actually covers everything in finding the values delta y and dy. But then we want to change. We want to compare how much difference, okay, how much error do we get when we move closer or away. In this case, question B, we move closer to the point when we are expecting that the dy, the one that we use to approximate delta y, should get closer to the actual value, or the difference is very small between delta y and dy. All right, so let us just focus on question A first. Okay, first we want to compute delta y. So there are a couple of things that we need to find first. The first one is f2. Okay, remember the formula, we have fx plus delta x minus fx. Okay, so to get the delta y. So first we need to find f2. So you just plug in 2 for this equation. Then you get that the value is equal to 9. Okay, so that's settled for this one. And then we want to compute this one, 2.05. Okay, so you do the same thing. You plug in the value 2.05 to this function, and you are going to get 9.717625. So if you want to go further, feel free to do so. And then from here, we can get the delta y. That is, just take this one minus this one. That will give you 0.717625. Right, so we get the delta y. And now we want to find dy. Okay, like I said, you don't have to compute lah gx plus dx minus gx. We just use the formula. That is dy equal to f prime x dx. Okay, and of course, we have to extend a bit this formula, meaning that we need to find the derivative. Okay, because we have f prime x in this formula. So differentiate this one, x cubed, we are going to have 3x squared plus 2x minus 2, 1. Nothing happens, become 0 upon differentiation. So this is the formula that we are going to use to compute dy. Actually, for both a and b, we use this formula. Just that the value for dx is different lah. For case A, we have 0.05. For case B, we have 0.01. So here, we have to consider the point that we want to compute when x equal to 2 and dx or delta x equal to 0.05. So we are going to have dy equal to, put in the bracket here, 2 square plus 2 times 2 minus 2. I need to put the square bracket to be consistent. So dx is 0.05. Then you just press your calculator. You get that the value for dy here is 0.7. So now we want to make comparison. Okay, the difference is 0. This one is still 0.17625. So that's for question A. Okay, that's one of the objectives lah. We have compare the values of delta y and dy. And then I hope you can try to do for question 2. So I'm just going to write what is delta y and what is dy for question 2, because they are basically the same thing. Okay, just that now we have 2.01 instead of 2.05. Okay, so for question B, if you calculate delta y using analogous procedure that we have here, okay, you will get that delta y is equal to 0.140701. Okay, and then dy, okay, upon calculation, you'll get that it is equal to 0.14. So the difference between these two values, delta y and dy, will be 0.000701. Okay, like I said earlier, for part B here, the point that we are considering, 2.01, is closer to 2 than the part A, 2.05. Then it is obvious that we have the difference. Okay, for this one, question A, part A is bigger than when we consider part B. And that is acceptable lah, because we are actually considering point closer to 2. Okay, meaning that the closer you get, the better the approximation that you are doing. Right, so I guess that is pretty clear. Right, so let's move forward. Okay, so we have one more examples that we want to illustrate the use of differentials. Okay, we have dy and dx just now in estimating the errors that occur because of approximate measurements. So this actually is very useful in your real life, especially when you go to industry. You have a lot of measurement tools that got some errors or some uncertainty. You have like vernier calipers. Even if you're using a so sophisticated technology, okay, there will still be errors. Even be in nanometers, in picometers, even smaller than that, there will still be errors. And of course, there are region of acceptable errors, a range of acceptable errors. Yeah, and that is being applied everywhere lah, in our real world problem. Right. So let's take a look at this example. The radius of a sphere was measured and found to be 21 centimeter with a possible error in measurement, okay, of at most 0.05. So that's the error that we are considering. Okay, what we use that for? Of course, we are going to use different variable here. Not only x and y. Okay, we are going to use the more appropriate. For example, when we discuss about volume, we want to use V, okay, so that people outside the area of mathematics can understand our work. But if you are just working with mathematicians, then so okay, you define the variable. Okay, you define the variable and you use that, no problem. But sometimes people outside mathematics, they don't really want to mingle with all that complexities. Okay, using specific X and Y only. So you use something that is closer, that is more familiar to them. All right, so continuing here, what is the maximum error in using this value of the radius to compute the volume of the sphere? All right, so now we need to specify the variables that we want to use. So let's say the first variable that we have here is the radius of the sphere, right? So I'm going to, okay, this one is similar to x, but now we use something that is common for people outside mathematics. We use r, and let r be the radius of the sphere, and then the volume, okay, the final output that we want to measure, the volume, we put as V. Okay, and I guess you guys still remember that the formula to find volume of a sphere is given by 4 over 3 pi r cubed. Okay, this is good. Maybe we can use this in test. I don't know. All right. And if the error in the measured value of our radius, okay, so what will be the notation for that? Okay, we have radius r, so the error will be dr. So I'm going to put like error in measured value r, we use dr. So dr here is the independent variable, so dr is practically delta r. Right. Then the corresponding error in the calculated value, so this is the formula that we use to compute the volume. So error in computed or measured volume, okay, that obtained by using this dr will be delta v. Right. So now you can relate, right? We have dx and delta x, and also we have dy and delta y. So here is the same thing. You have dr and delta r. You have v and delta v. Okay. So from v here, you can get the dv lah, from the formula. Okay, dv f prime v times dr or delta r. So that is what we want to compute here. All right. So let us just write the formula for dv first. So dv is equal to, okay, you can do the differentiation here, okay, and multiply with dr. So 4 over 3 pi r cubed. Perform differentiation with respect to r. So you are going to have 4 over 3 pi r cubed. So let me write 4 over 3 pi. Just put it there first. This is the one that we want to. This is just a constant. So you have 3r squared. And then you multiply by dr. So here you can cancel one another. So what left you is 4 pi r square dr. So this is from the formula dy that we had earlier. Now it is being used as dv. All right. So now, okay, we have that when r equal to 21, okay, and dr or delta r is equal to 0.05. That is the error here. So we can compute the value of dv. Okay, so dv is equal to 4 pi, r is 21. So we have 21 square, sorry, this one, times dr, 0.05. So you get a very long value, but I'm going to take the big one only, that is 277 centimeter. All right. So, do we need to compute delta R? No, we don't really need to compute delta V, but no, this is the resultant, okay, the maximum error. dV here is the maximum error. The maximum error in the calculated volume is about so that's the value that we want to obtain, because now we are using dV as the approximation of the actual error. Okay. If you want to find delta V, you can find it as well. Okay, where you can compute the value when R is equal to 21 and R is equal to 21.05 cm, right? But because we are dealing with real life problem, sometimes it's not possible for us to get the actual value for delta V, so we can rely to dV as an approximation of the error. So that is what we are doing here. All right. So it might look big to you, 277 cm cube here. But again, when dealing with real life application, we rely on relative error.